My apologies. This video is going to be painful, both because of its length and because of the confusing ideas. And I hope we will sort out the confusion when we get back together. But you need to wrestle with it now. The hook. Why does a figure skater spin faster when she pulls in his or her arms? And it is a matter of conservation of angular momentum. We will use an L for angular momentum, lowercase or uppercase. This year, next year, we will, in AP Physics, we'll make a distinction between them. Remember that translational momentum was mass times velocity, and that translational momentum was conserved if there were no external forces, if you have an isolated system. Well, so too. Angular momentum is going to be conserved if there are no external torques, and instead of this inertial quantity times translational velocity, it's going to be rotational inertia times angular velocity is what we mean by angular momentum. So here is an application that you have this frictionless table. This mass has a string pulling on it, but that force does not produce any torque. It's only radial as this thing spins around in a circle, and so it is valid to say that the angular momentum will be conserved, and I would expect you to state that and then justify it. And by angular momentum we mean I omega, and in this particular case, since this mass is at an arm r, I would use mr squared for the rotational inertia, and for omega I'm going to use v divided by r. And if you put in the values that were given here, I think you will find it is possible to get what the final velocity will be. Of course, if the table were not frictionless, then you would have friction, and friction would act tangent to the circle that it's going around in, and so it would be a torque, and so there would be an external torque, and angular momentum would not be conserved. Again, that you need to realize that these people walking in towards the center is not going to be an external torque, and so angular momentum is conserved. State it. I'm going to do this problem in terms of the conservation of angular momentum, and justify it. Yeah, I'm pretty convinced there are no external torques as these people walk towards the center. And then just what is the angular momentum at the beginning, and what's the angular momentum at the end? And you have the angular momentum of that person's mass times their radius squared times omega, plus the angular momentum of this person, plus the angular momentum of the platform that they're standing on, which has some rotational inertia. I'm trying to find it, and it's spinning at 10 radians per second. And then at the end, this person here is now at 5 meters and spinning at 40, and the other person is at 3 meters spinning at 40, and the merry-go-round is spinning at 40, and so I is the only unknown you can solve for, and I ask you to do that. New topic. A frisbee coming towards you, rotating like this as it comes towards you. If you smack it on the leading edge, oh, come on, I don't have time for this. If you smack it out here on the leading edge, push it straight up, what in fact will happen is that this edge will go down. Push up here, this edge goes down. That's pretty freaky. That's worthy. The frisbee is going to twist like that when you push up on this edge. Well, that's worthy for us to worry about. And I hope that you will master this. You will be expected to have mastered it. Several details. First off, you pushing on this edge at this distance from the pivot, out at the edge, at a distance of the radius of the pivot out, you pushing straight up, and this is a little bit off to the angle so you can see that vector back there, pushing straight up with a force is going to produce a torque. It is not acceptable for us to call that a clockwise or a counterclockwise torque anymore. We need to get the direction of the torque. And the way you get the direction of the torque is using this right-hand rule. You will put your shoulder, your right shoulder, so that it is at the pivot. Extend your arm for the torque arm. So you put your right shoulder at the pivot, extend your arm for the torque arm, and then you keep your arm pointed in that direction, but turn your wrist so that you can make your fingers point in the direction you would like. In this particular case here, I want my fingers to be pointing up. So the first is the arm vector, and then this force vector. And if you do that, then your extended right thumb indicates the direction of the torque. It's very awkward, but that's the way it's always done. If you have any pair of vectors, it doesn't have to be arms and forces yielding torques, any vector A crossed with a vector B will yield a vector C, and the direction of the vector C is given by this right-hand rule. You put your arm in the direction of the first vector, and then turn your wrist until you can wrap your fingers in the direction of the second vector, and your thumb gives you the direction of their cross product. So, this one here, I want everybody to stick their arm behind you. You have to turn your waist a little bit so that your arm, your shoulder is at that center of the pivot and your arm is extended in the direction of the arm. So point your arm away from this screen, and then you can turn your wrist so that your palm points up, or your palm points down, or your palm points to the side. Keep your arm pointed to the back. In this case, we want our palm to point up. And if you do that, then you can wrap your fingers up, and I think you will find that your thumb is going off in this direction. That the torque is in that direction for this force acting at that arm. Well, if the torque is in that direction, then the angular acceleration is going to be in that direction, off to the left, which means the change in omega is going to be off to the left. Now we need to stop. We have figured out, using this right-hand rule, the direction of the torque, and so the direction of the change in omega. Now we have to go back and get the direction of omega. And that comes from your right hand, but this time you make a loose fist with your fingers so that they curl around, and you make the curl of your fingers of your right hand go in the direction that this thing is turning, and then your extended thumb gets you the direction of omega. So here is an awkward picture where this is the back of my right hand. My fingers are curling to try to mimic this curl here, and your thumb should be pointing down. There's my thumbnail. Thumb pointing down when you do that. Will you please try to mimic that? That you take your finger and wrap it, and you should see your thumb pointing down. And what, get this, such an ugly picture. Come on. which means that omega is going down. It has nothing to do with this whole torque and delta omega stuff. That was due to the force. It has everything only to do with this direction of spin. So omega is going down. But the change in omega we've established is off to the left. And if you add that change in omega on to this initial omega plus change in omega, there is final omega. And if final omega is going that way, then that means that this disk is now oriented that way. I'll take the green arrow. Come on, green arrow. If the disk, if its omega is like that, then it's turning like that, which means the disk has dipped. There you are. That's very complex. I expect you to be able to do it, but not without a whole lot more practice. Speaking of more practice, here's another problem. I'm going to take a bicycle wheel that is turning like this. It's got an axle on it. I'm going to put a string here so that that will hold it up, that I'm going to exert a force upwards holding that string, and that force will be equal to the weight. So we're going to have translational equilibrium. This wheel is not going to go lower. But if this is the pivot, that's the point that it tends to rotate around, then you need to put your right shoulder there, extend your right arm off to the right, parallel to this bar, and then turn your wrist until your palm is pointing down so that you can wrap your fingers down, and I think that you will find that your extended right thumb is going into the page. This looks like it's going off at a diagonal, but it's meant to represent straight into the page. So the torque is into the page. So the change in omega is into the page. Now we need to get omega. Take your right hand in a loose fist, make your fingers curl in that direction, and your thumb should be pointing off to the right. So omega was going off to the right, but it changes into the page, and what you will see is this wheel will turn, it will not rotate down, it will turn around in a horizontal circle. It is magical. It is called precession. That's turning. And you will be able to predict it. New topic, equilibrium. I want this to be in total equilibrium. That is both translational and rotational equilibrium. Right now it is not. It's got 90 newtons up and 40 newtons down, so I need an additional 50 newtons down. What force would I add to this to get total equilibrium? Well, for starters, translational equilibrium means that the net horizontal and the net vertical forces are zero. There is no horizontal forces here, but vertically I had these three, and so if I add on 50 down to them, they will add up to zero. So there is my equilibrium force, but where to put it? To have total equilibrium, I also need to have rotational equilibrium. I choose to put my pivot at zero, and so I have the following torques at this time. That at an arm of 30 centimeters, I have 70 newtons up, so arm, cross force, that gets me that torque. Note, if you stick your shoulder here and extend your arm to the right, go ahead and do it, and then curl your fingers up, your thumb is coming towards you, and we call that a positive torque. This one here, if you do it, you'll find your thumb is going away from you, hence a negative torque. Another positive torque, and then this one, because it is going down, I presume it's going to be another negative torque, but I don't know where I have put that 50. And if I solve for L, it comes out to be 42, which means that at 42 on this bar, 42 centimeters, if I put 50 newtons down then I would have total equilibrium. Now I want you to do it. This time I'm putting the pivot at the 100 mark. Well, that's very nice. That means there'll be no torque from this one because its arm is 0. Very cool. These are the same forces as before, so again it's going to be 50 newtons down, but the question is where to put it. And I would ask you to do those calculations, stop the show, do the calculations, we start the show again, and I hope that the answer you got was 58 centimeters. But that's 58 centimeters from the pivot. And if you go 58 centimeters back from 100, you're at 42 again. The fact is that if a system is in total equilibrium about one point, then it is in total equilibrium about any other point along the line of the rod. That's very useful. You will use that in a lot of problems that you do. Again, I want you to find the equilibriant force. And this one is a little awkward because this one is going off to the side, but it's the same idea. I want all of the horizontal forces to add up to 0, and all the vertical forces to add up to 0, and all the torques to add up to 0. Well, I'm going to do this for you, that 10 newtons, 30 degrees, this is going to be 5 newtons, that's going to be 8.77 newtons. So my equilibriant force, I'm going to need to have 8.77 to the right to get horizontal equilibrium, and I'm going to need an additional, if that's 5 and that's 20, I'm going to need an additional 15 newtons up. So I would ask you to do the trig of figuring out how big that hypotenuse is and what angle it goes at. Yeah, you can do the angle away from the vertical, or you could do the angle away from the horizontal. There is your equilibriant force, but then the question is where to put it on the bar. I strongly recommend that you always choose 0 as your pivot, and that will get rid of any torque from the 10 newtons. You could also choose 50 as your pivot, but then it's going to be how far away from the 50, and that's going to be one more calculation to figure out what that means as far as your position along the bar. Finally, here is a problem in need of equilibrium. It has translational equilibrium now, but it does not have rotational equilibrium. And if you add a force to try to get it to stop spinning, then suddenly it's going to be out of translational equilibrium. That those two equal and oppositely directed forces that are not collinear form what is called a couple, and the only way to get equilibrium in the presence of a couple is with another couple. That I could make this be located here and 40 newtons up, and this be located here 40 newtons down. That would be another couple, and I would have total equilibrium. But I could also make both of these be 80 newtons, but at half the arm that it goes at 30 here. And again, I would have about a pivot there. I would have a rotational equilibrium and translational equilibrium. And of course, if you have total equilibrium about a pivot there, it is in total equilibrium about a pivot anywhere else. Thank you.